Next topic is stochastic approximation to gradient descent. We know that the gradient descent, it has been applied in order to find out the best weight by decreasing the error or by obtaining the global minimum error. So when we obtain the global minimum error, we get the best weight, and thus whatever the output that is being obtained, that is a predicted output, it is equal to an actual output when the error is equal to 0. Then we say that we got the best output. So now we are applying a stochastic approximation to a gradient descent. So first understand the meaning of what is a gradient descent, what are the formulas we are using in a gradient descent. Next we'll see the stochastic approximation to a gradient descent. So we know that if we consider a gradient descent, a gradient, it is nothing but a smallest change, and a descent, it is nothing but a decrease in a error value step by step. So we are going to move with the larger steps when the error is more, and when we are near to a global minimum, or when the error is about to decrease, we move in a smaller steps. At that time we got a parabolic graph of a gradient descent. So now let's understand the difference between a gradient descent and a stochastic approximation to a gradient descent. So initially we know that in a gradient descent, this is an artificial neural network. So we know that we'll be having an input x1, x2, x3 up to xn are the inputs. W1, W2, W3 up to Wn are the weights that has been assigned for this inputs. X0 and W0, X0 value we are going to consider it as 1, and W0 value we are going to consider a standard value. So we know that we are going to multiply an input with the weight, that is x1 into W1, x2 into W2, x3 into W3 up to xn into W1. We are going to multiply it together, and correspondingly we are going to add it here, summation. So that's why that the output of this summation, it is called as a net value. So this net value, it is equal to a summation of I equal to 0, since the value of x0 and W0, it is starting from 0 to n, xi into wi. So now here we have n number of samples. Suppose I consider a 3 sample example of predicting the height. So that is a previously solved example in a visualization of a gradient descent. If you go through that video, then the problem has been solved by considering a 3 samples where we are going to predict the height. So now if I consider the 3 samples of an input, then it is going to start from x0, x1, x2 and x3. So where x0 and W0, it is going to take the standard value, and x1, x2 and x3, it is going to take the 3 samples value. So all these samples are, now if I apply a gradient descent method to this artificial neural network, so initially we know that in a gradient descent we are going to choose some random weight. So we doesn't know an exact value of a weight initially, so we are going to choose some random weight, that is wi, and delta wi, it is going to be made to 0 initially. This is as per the gradient descent algorithm. So delta wi value, it is going to be 0, and wi value, it is chosen randomly in a gradient descent method. So now wi, it is going to take from 0 to 3. So since we have a 3 samples here, so 0, that is W0, W1, W2 and W3, it is going to take, and then it is going to multiply, it is going to perform the summation of it, and then it is passed through an activation function, and we are going to get an output. So the output, suppose this is for a single neural network. So in between there can be a many hidden layers. Suppose if I consider, so many hidden layers are present. So this net, it has to go through many hidden layers, and then it is going to reach an activation function at the output side, and finally we are going to get the output. So in an output, if we find out the error, it is nothing but error, or the residual here, it is nothing but the sum of the squared errors we are going to do. The sum of the squared errors is nothing but we are going to consider each and every sample, all the 3 samples errors are added together, and finally we have got the sum of the squared errors. So now this sum of the squared errors we have considered, and if the error is more, then we are going to backtrack it and increase the value of an weight to some delta value. So at that time we know that initially we have kept delta wi value to 0. So now we are incrementing a delta Wi value to some value, say around 0.1. So now the older value of a weight, the initially whatever you have assumed, that weight plus 0.1 whatever step value of an weight I have considered. So that value, it is been added and it is assigned for all the 3 samples. And then again it is summed, and again it is passed through an activation function, and again we are going to get the sum of the squared errors at the output. Now we are going to compare it with the previous error. Suppose if it is still more, then again backtrack and increase the value of a delta Wi, and again the new value of a weight is assigned. So this process is continuous in a gradient descent until we get an error value it is equals to 0, means until we get a global minimum value of an error. So this process, it is going to be continued. So this process is going to take larger time. So the computations are more in a gradient descent. So to overcome the computations, we go for stochastic approximation to a gradient descent. The stochastic approximation, the name itself indicates, stochastic means randomly it is going to choose some training example or sample. So what we have assumed in our example, we have assumed in predicting the height, we have assumed we have 3 samples. So out of the 3 samples, if I apply a stochastic approximation, the weight is assigned, instead of assigning to all the 3 samples, it has been assigned to any one of the sample, and that only one sample, it is being processed to get the output, and we find out the error for only one sample, randomly chosen sample, rather than for the sum of the squared errors like in gradient descent. So what we are going to do in stochastic approximation? In stochastic approximation, we are going to choose a random weight, random sample, we are going to choose it. Any one sample we are going to apply the weight, rather than for all the sample in a gradient descent, and we are going to process it, and we are going to get the output. Depending on that output error, we are going to approximate the error for all the other samples. So this is a stochastic approximation. Now why this stochastic approximation it has been performed is in order to reduce the computation, because we know that a gradient descent, it is applied to an infinite hypothesis space. So what is an infinite hypothesis space? It is explained in the previous video. So infinite hypothesis space or a larger hypothesis space is the one where we have many number of hypotheses or the prediction of a weight. So where there is no boundary, since we are considering the weight value up to an n samples, so that's why we have an infinite hypothesis space in a gradient descent. So the computation is very difficult. Whereas if we apply a stochastic approximation to a gradient descent, everything is going to remain the same. Only one changes. Instead of considering all the samples in a gradient descent, in stochastic approximation, any one sample is been considered randomly, and for that the weight has been assigned randomly, and again the processing steps are being continued, and we are going to get the output. And depending upon that error, we are going to tell the error of x1 is so much, the error of x3 is so much. Without calculation, we are just approximating an error. So that is a stochastic approximation. So let's see the formulas of a stochastic approximation and a gradient descent. So in a gradient descent, we know that delta Wi. So what is the rule actually here? The rule actually is, we know that it is how the weight will be updated. The weight will be updated as Wi, it is equals to Wi plus delta Wi. Correct? So initially this delta Wi would have been kept 0. Only delta Wi, that too, it is not a fixed value. So randomly we are going to choose some value. We are going to perform the processing. So and then when backtracked, so this delta Wi value will be calculated. How delta Wi value will be calculated? It is by this formula. The formula is eta summation of d belonging to d, td minus od into xi. So you can observe here, we have a summation here, means we are considering or we are assigning the weight value for all the training examples or for all the samples. So this small d indicates that it is a training example. So suppose if I consider a database of an Enjoy sport, what is explained in the class, we know that we had around 4 rows and 6 columns. So the complete 4 rows and 6 columns, it is considered as a database, that is nothing but a capital D, whereas a small letter d, it indicates an one particular training example. Suppose if I consider the second row of a data set, then it is nothing but what? It is nothing but an one particular example of a data set. So in a gradient descent, if you are calculating the weight delta Wi, so that delta Wi, it has been added to the old value of a Wi, and we are going to get the new updated value of a Wi, and this updated value of a Wi, it is assigned to all the inputs. It is assigned to all the inputs. So this is the gradient descent method, where you are applying for all the training examples. Whereas in a stochastic gradient descent, randomly we are going to choose some data value. So that's why, or randomly we are going to choose a particular training example. So that's why we don't have a summation here. Everything is going to remain the same. Now what is TD? TD, it is nothing but here it is an target output of a particular training example. OD, it is an output of a particular training example. XI, it is an all the inputs. So whereas here, and eta is the learning rate. So eta is the learning rate, same T is an target output, minus O, it is an output, XI, it is an input. Observe here we have considered the sum of the squared errors. So here we are considering the summation of all the errors. So here there is no summation, only one particular training example it has been chosen. So this is a stochastic approximation to an gradient descent. So you can see here the explanation is same. So the idea behind the stochastic gradient descent is to approximate this gradient descent search by updating the weight incrementally. So you can observe here the idea behind the stochastic gradient descent is to approximate this gradient descent search by updating the weight incrementally for each individual example by using a formula that is delta Wi, it is equals to eta T minus O into Xi. So what has been explained here, the same thing it is explained in the PPT also. Next slide. Our next topic is, it is an stochastic approximation to a gradient descent algorithm. So we have seen the gradient descent algorithm. Now what are the changes we are doing to a gradient descent algorithm? It is being seen here.